Hi everyone. My name is Mike Drogalis, and today I'm going to be talking about Onyx. So I am the person who created Onyx. I started working on it about a year and a half, 2 years ago, and I'm just totally delighted with the progression in terms of how far it's come and the community support and all those things. So thank you for coming. So I've spent the majority of my career, almost my entire software engineering career, writing products for distributed data processing. I've worked in real-time streaming for the financial sector. I've done business intelligence, batch analytics. I've done pharmaceutical data warehousing, ETL, data syncing. I've done all these things and used the majority of the modern tooling. And I was profoundly disappointed with the way that those tools are exposed to the developer and the model that you work in. I just wasn't getting a good enough return on my investment. So I had to build something else to do this myself, and I had to be able to do everything that I was doing before, all those things that I just mentioned. So this is Onyx is a cloud-scale distributed data processing platform with a core piece to do this compute model and then supporting tooling around it. And the main idea about Onyx is that we've taken the traditional computing model that you find in MapReduce, Spark, Storm, and all those other things, and we split it apart into smaller building blocks, ones that can be recomposed and put back together for more flexible, robust programs. Another goal of Onyx is to offer a hybrid batch and streaming API via the exact same API mirrored that you would be using otherwise. We're finding more and more in applications that you're going to need both of these things to be successful, to be truly fault tolerant at your data application level. So this was a goal we were trying to tackle. In terms of its design, Onyx is masterless, and this is almost fully unique among other platforms in this space. And we're going to talk mostly about why masterless is kind of important today. And probably of interest to this room is that it's Clojure all the way down. It's written in 100% Clojure and primarily intended to be consumed in Clojure. Even though we have stories for other languages, this is really its sweet spot. So this talk is going to be divided into two parts. Very briefly, I'm going to cover the API value proposition and why you'd want to use it as a developer and what it gives you. But we're really going to do a deep dive about that in the workshop, and you're going to learn how to use it and things like that. Most of the talk is going to be about the design and how Onyx actually works, because I don't get to talk about that very frequently. And it's really something you ought to know if you're going to take this into production. So let's talk about the API a little bit. I like to talk about moving my data in terms of workflows. We like to draw these out as directed acyclic graphs and picture our data moving along these edges in the graph. So at the top, we might be reading some tweets or some metrics and then applying any number of transformations and aggregations in the middle, and then writing our results in the end to some kind of storage medium. In Onyx, we model this structure directly using a vector of vectors, and this is called the workflow in your Onyx job. The keywords are tasks, and you see the mapping from left to right is a source task to a destination task. This is strictly capturing the structure of your computation, and this is one of the first things we take out of the larger, complected computing model. It's really important to isolate this. But structure is not enough. We have to relate it to context for what these tasks actually mean. And the catalog is going to provide that context. For every entry in the catalog, every task, you're going to give it a name, so it corresponds to a particular entry. And we give it some functional and non-functional parameters. For example, in the lower one, in the parse payload task, this is something that's functional and presumably transformative. We bind it to a function. Specifically, we give it a fully qualified namespace keyword that we resolve to a Clojure function on the class path at runtime in your cluster. We presume this is going to be there, and we look it up. And then we could, as you see, we give it other parameters like a batching size, and you can do all kinds of tuning at this point. In terms of actually doing these transformations, this is straight Clojure. We're going to resolve a normal Clojure function that's going to take a map, and it's going to return a map. We call these maps segments for a specific reason. But you notice that this isn't a macro. There's no like surrounding context, or like it doesn't need to be in any specific place. This is a plain Clojure function. And this is really important because these are the three primitives that you use to build Onyx programs. You use workflows, catalogs, and functions. The API is wider, but this is the trend. We're aggressively using data structures to be able to be significantly more flexible than a lot of other platforms. And that's kind of it for using the API. We're building on these primitives all the time. And despite them being very simple, this is incredibly effective. And that's actually all I have to say about the API for now. We're going to learn how to use it more in depth later. But for right now, I want to talk about how we do messaging in Onyx. So when I talk about messaging, I'm talking about peer-to-peer asynchronous communication. This is direct, and we're guaranteeing that messages will eventually be processed by the Onyx cluster. So the way that we went about this was actually by directly adopting the algorithm from Storm, if you're familiar with that. So as I know, this algorithm was invented by Nathan Mars a bunch of years ago, and so my hat is off to him. This is all his work. I'm just reproducing it and showing you how it's done. And the genius in this algorithm is that for every message that's floating through your cluster, we're only using 20 bytes in memory on something that we call an acking daemon to track the state in arbitrarily long workflows. So no matter how long or dense your workflow is, we're only going to use 20 bytes per message. And the implication is that you can have hundreds of millions of messages pending on finishing in your cluster concurrently. So that's a little fuzzy, but I'll put it into better context. If we have a workflow like we had before, this workflow is mapped to a specific topology, if you will. Peers are the agents of execution in Onyx, and they sign up for tasks. So as a peer grabs a task, it's receiving subsegments from an upstream peer, and it's directly emitting transformed or aggregated segments to downstream peers. This isn't brokered. They don't go through third-party communication. This is actually how we go fast, because it's just point-to-point communication. So what do I mean when I say like sending a message through a cluster? We like to think of these segments as turning themselves into trees. When a message or a segment initially enters the cluster, we call this the root segment because it's a little bit special. So if a task receives a segment, presumably it's going to emit 0 or more segments. So say task T gets this payload and produces 2 more segments downstream. Downstream tasks can choose to either just not emit anything else and they're done because they're leaves in the workflow, or they can emit more segments, as we see. Once we've successfully processed all these segments and done whatever we need to do, be it talking to a database or writing to a WebSocket or whatever, we call this segment tree fully processed. And this is the guarantee in Onyx. We're eventually going to process all the nodes in this tree, and we need to have the infrastructure behind it to make sure that we're really going to do this. So how can we guarantee that? Well, this algorithm it's actually very simple, but it's a little tricky to explain, so I'll try to go slowly. The root segment is assigned a random 64-bit sequence. This is an uncoordinated assignment. We generate it in isolation, and the chances of later collisions with different numbers is very low because this number is so dense and dependent on its position in the tree. We take this sequence and we assign it to the track state. This is on a different machine in memory. This is that 20-byte thing I was talking about. And we directly correlate that to the state for the first stage. The brackets is showing the succession of the state as we go along. So when a segment produces new segments, we assign those new segments their own random 64-bit IDs, and we update the state. Now, it's not obvious why the state is this particular value now. So we have to go back and roll it back and look at it a little bit more carefully. So the first segment, segment 1, the root segment, had a particular bit sequence which directly corresponded to the first state. The second state is the result of using the exclusive OR operation. It takes as parameters the previous state, the segment that has been acknowledged as completed, which is the root segment in this case, and the bit sequences of all the new segments that it created. If you exclusive OR all 4 of these things together, you notice that the first 2 cancel out because anything exclusive OR itself is 0. And this is the fundamental compacting property that lets us stay around 20 bytes for the entire track state. So the rule is whenever you finish a segment, send the acknowledged bit sequence plus any new bit sequences and exclusive OR all those together with the previous state, and you'll get some sort of compaction going on. So we'll keep going to demonstrate what's eventually going to happen. So as these segments complete, and keep in mind that this is distributed concurrent on different machines, so they're going to be happening at different times, and these operations are going to commute, so it's OK. This segment happens to not generate any new segments after we've completed it. So green means we've acknowledged it. We update the track state to -135, et cetera, and we see that this is a really simple operation. We just take the bit sequence that was applied to this segment, and then we exclusive OR it against the previous state. And you'll notice that this phenomenon now happens, that the new track state is directly equal to the bit sequence on the leftmost node in the tree. And that's because the top node and the rightmost node have had their bit sequence IDs sent to the acking daemon exactly twice. So they've canceled out, leaving only the unacknowledged bit sequence left in the acking daemon. Because all these values are exclusively OR atomically, there's no chance of a race condition happening where it sort of sees like half a value or something like that. And you probably get the idea, but it's interesting to plow all the way to the end. It creates 2 new segments, assign them random 64-bit IDs. Eventually, we acknowledge that segment, and you see the direct, again, for the first 2 arguments to bit exclusive OR are the same, so they're going to cancel out, and you're going to get a new track state, and you're going to use those 3 expressions and XOR them together. Now let's say that the lower right one completes. You see the phenomena again where the one on the left is actually equal to the track state because all of the other nodes have had their bit sequences sent to the acting daemon. Finally, that was basically what I just said. Finally, you're going to get to the last one, and you're going to get a value of 0. And the reason is that we take the previous state, negative 9177, et cetera, and we exclusive OR it against the last segment. At this point, every segment in the segment tree has had its value sent to the acting daemon twice. Hence, everything has been exclusively ORed itself twice, so we get 0. And 0 is the magic value that we're looking for. That's how we can know for sure that the whole tree has been processed. And you might ask, well, what happens if there's a failure? Because, of course, that's going to happen. Let's say a peer disconnects when it's processing a segment. It was able to receive it, but it was not able to emit it and say that I've completed this specific segment. What's actually happening is that the root segment is a little bit special. It's hanging on to that segment, and it's waiting for the acting daemon to send in a message saying, I found your message ID, which is held consistently throughout the tree. They all share a common identifier. And if it doesn't hear that within the pre-configured time, say 60 seconds, it's just going to replay that segment tree all the way through. And this is why Onyx is an at least once data processing system, because it heals itself by replaying. So functions need to be idempotent to deal with this. And then you might ask, well, what happens if the root segment dies? Well, this algorithm presumes a special property of your input storage in that most queues have some sort of take a message and then acknowledge it when you put it back on the queue, or when you are actually finished and you take it off the queue. And if you disconnect, the message goes back on the queue. So this is what's happening at the root. If you pull off a message and the root node dies, the message just goes back on the queue or whatever related storage that can simulate that, and another peer is going to pick it up and then replay the whole tree. So you have fault tolerance at every level in this processing system. OK, so that was messaging and direct communication, and I don't want to conflate that with what I'm going to talk about next. We're going to talk about coordination now. So in messaging, peers talk specifically to one another, and they only use segments to communicate. The rest of Onyx's design is about coordination, and it's a masterless approach with a log-centric design. And as opposed to using Storm's work here, this is almost entirely my own work, of which I'm very proud because this is unique. And it's going to leverage Zookeeper's primitives to get its job done. So its architecture from a different angle looks like this. Peers do not talk to one another unless they have segments to send over the wire. Otherwise, everything is going through Zookeeper, everything. And that's really important. So if we look at this from the perspective of a particular peer, a peer is going to boot up, and it's going to give itself an empty replica. All peers have a replica, which starts out as an empty Clojure map. The log is a sequence of entries. These entries are Clojure functions to be applied to the replica, which means that the replica has specific state succession semantics. So at any given point in time, the replica is immutable as a specific logical clock value. And we're continuously starting at 0 and applying these log entries to the replica one at a time. And these entries, these functions that we're applying, are pure deterministic functions. They're going to be the same as of any particular entry. So if multiple peers read up from entry 0 to entry 4, they're all going to have the same replica. And this is a super critical property for correctness. So the interface to the log and to the replica is actually only 4 functions, 3 of which are pure. So a peer can either take a log entry and apply it to its replica and give it a new replica. It can take the difference between 2 replicas to tell me what happened between 2 points in time. It can take an entry and append new entries to the end of the log as a reaction. And the only side effecting function that it can perform is literally to perform side effects based on an entry, we've isolated that in a specific part of this design. And this is quite powerful to use in practice. So when a peer boots up, it starts reading. It starts at entry 0 and then proceeds to entry 1, 2, 3. And you see its replica, its Clojure map being updated. And the replica serves as a view of the cluster, some structural information telling you who's doing what and other non-segment behavior, if you will. And all these peers are doing this at the same time. They're reading at independent timelines. This isn't like peers 1, 2, and 3 all have to be on entry 1 and then entry 2 and entry 3. They're just going to boot up and zip along at any given rate, and presumably some of them are going to lag behind, and that's fine. But the trick is that as of entry 4, if all 3 peers happen to be there, they're all going to have the same value because these are pure deterministic functions. And as I was saying before, this is just an example. If you read an entry, you append entries. This is a reactive thing. So what's really an important part of this design is that peers, these agents of execution, don't just decide to do things of their own accord without informing others. They actually read things that might influence them to do something and then append an entry as a proposal to the end of the log. The peer doesn't even do anything when it proposes. It actually has to play forward to the entries that it appended before it can make a decision. And the reason that that's important is because all peers will get to that proposed entry and come to the same decision that that peer would have made anyway, because they're sharing pure functions. So it's like everybody knows what everybody else is doing. So there's 2 very interesting ways to look at how we use the log, and that's how we add and remove peers to the cluster. So if new machines come online or come offline, how do we handle that? Because there's no central master. Well, what we do is we keep information in the replica. This is a very small part of the replica as of logical clock value 45. We call this the pairs. And Onyx uses a ring-centric approach to doing failure detection. So those arrows denote that peer 1, for example, is watching peer 4 for failure. So if it fails, it can sort of do something about it. And this is a one-to-one mapping. Everyone's watching only one other person, so we always try to maintain the ring. So peer 5 shows up. It's like, hey, I want to join your cluster. Cool. Peer 5 starts off by writing a log entry to the end and says, hey, I'm a new guy. Check me out. And based on a hashing function, let's say peer 1 is kind of the chosen one to react to peer 5 with some side effects and actually attach a watch via Zookeeper to peer 5. Everyone else knows that peer 1 is the one who's supposed to do that based on these pure deterministic functions that are going to hash the current nodes together and figure out whose turn it is. As a reaction to this happening, peer 1 is going to write another log entry. This is a 3-phase join. This was the prepare phase. When peer 1 writes a new log entry saying, all right, I've added the watch to peer 5, cool, we're ready to go, we enter the accept phase. Peer 5 reads this because it's looking for this entry to occur. And as a reaction or as a side effect, it's going to add a watch to peer 4. And if you look at the shapes now, we have the ring as before, but we've also created a triangle on the outside. And you see what we're about to do, because peer 5 is now going to write a log entry and say, I've been accepted into the cluster. And if you look at the replica towards the bottom, we have this information logged. It's stable on all peers in its local replica. Finally, peer 1 is going to read this log entry, and it's going to drop its extraneous link to peer 4, creating the full circle again. So we've just taken it, made a little triangle on the outside, and then widened it back up. So it fires its side effects, and at that point, all the pairs have rebalanced, and you have a completed ring again. This is fairly efficient to join large numbers of peers together. It can churn through about 1,000 of them in a couple seconds. It's quite quick. And it can handle the case where any peer can fail at any given time. It will abort and back off and retry, especially if you have large numbers of peers trying to join at the same time who can't stably connect and form those sort of triangles that you need. So there's no contention because this is strictly ordered. Now that we've talked about that, failure detection is actually very easy because you know in the replica who's watching who. If peer 5 suddenly kicks the bucket, peer 1 had a watch on peer 5, so it knows when it goes down. What peer 1 can do is write an entry to the end of the log and say, I see peer 5 has gone down. Because we know who's watching who, peer 1 can inference who peer 5 was watching, and it can literally tighten the ring. So when that log entry comes down, peer 1 is going to fire some side effects and then just close the ring over to peer 4. And then the ring is totally healed again. Another very perceptive question is what happens if 2 consecutive nodes in the ring fail? This is actually really easy because we run through the same thing again. Peer 1 knows that peer 5 was watching peer 4, so it writes the log entry and eventually closes over. And then it just repeats the cycle again, except this time peer 1 immediately notices that peer 4 is down, so it writes a corresponding log entry saying, oh, peer 4 is down, we should do something about it. Peer 1 reads this and reacts knowing that peer 4 is watching peer 3 and then just tightens the ring again. So you can have very catastrophic failures where exactly half your ring fails, and a peer is just going to continually do reads and writes to Zookeeper and churn through the bad peers and evict them. And this is also pretty quick, even if you had a really nasty case of a specific part of the ring being chopped off. So this log approach is fantastic. I really like it that we came up with this, and we use generative testing extensively to ensure that this is correct. And what we do actually is we seed a number of log entries. We pre-create these to simulate scenarios that we're interested in, such as peers coming online and then rapidly dying at specific points in time. And then we bring up some peers and allow them to react to all these log entries. And we wait until no one has any more entries to append to the log. We assume all activity has ceased at that point. At that point, we collect the entire log, and then we zip it up and get a final replica and perform property-based assertions on that. And this is awesome because it actually creates your program like a time machine because you're able to move back and forth between the log entries and look for states that are leading you into something like weird. And you'll see how this looks. So if we were to run a generative test and we collected the log and we had 5 entries, say, we'd run through all of the entries on a replica and get a final replica and perform our assertions. And sometimes that works just fine. All our assertions pass and we're happy. But sometimes these assertions fail. What we do at this point is that we roll all the way back to the function 1 with the empty replica. And then via a REPL, I just step through each entry and I look at the replica and I look for where things are starting to go bad. So usually you go through a few functions. That looks OK. That transition looked fine. Ah, I found the bad transition. Now all I have to do is roll back 1 entry, patch the code, test it, make a unit test because this is a test of a pure function from a Clojure map to a Clojure map, get that running, make sure that transition passes again, and then just plow all the way forwards, and then my bug is fixed. And I do this hundreds of millions of times on our build, and we find things. We find really weird things that we would never find without this kind of technique. So log-based approaches are really great, and you should probably consider them for your designs if there's room for this kind of thing. I think this is a largely unexplored territory. But it keeps getting better because our scheduling algorithms that we use, since there's no master, peers need to decide what work they're going to do. Those are pure functions. Every time a new job shows up or a peer adds or is removed from the cluster, the entire schedule of who is executing what is rebalanced. And it's done in such a manner that we can take a static snapshot of the cluster and then look at really strange scenarios of what would happen if there were weird numbers of peers and very large numbers of jobs. How would our scheduler react? Other things we use that are a little bit more advanced, for example, is a coordinated garbage collector algorithm called Blade. And it's actually a scenario where peers are guessing when they're about to garbage collect, and when they are, they put a message on the end of a log and use it as a primitive broadcast system and tell other peers to stop sending messages to them while they GC. Because if a peer GCs while it's getting messages, your latency is going to shoot way up because that might be a pause of 1 or 2 seconds. And for some people, that's just totally unacceptable. And after it's GC'd, it can put a message back on the log saying, I'm game, start sending me messages again. It's the same with back pressure. We have some really sophisticated techniques to deal with this, but they're mostly using high watermarks and putting messages on the log when the volume of messages that they're receiving is higher than the amount of messages that they're able to emit. So they're able to dynamically adjust by communicating with upstream peers, telling them to clamp down on the amount of data that they're emitting towards them, and then incrementally increase as they go along. And this is a user-level thing. There are extensions and APIs for integrating with the log, and one of the great things that you can do is create CloudWatch alarms based on information in the replica as you're getting entries. So if you have too many jobs that aren't being worked on, make a CloudWatch alarm and auto-scale your Onyx cluster. You can do this. There's an API for this kind of thing. You can really run wild with all the possibilities here. So a lot of people ask, what kind of state is Onyx in? Is it ready? Can I use it? And I think it's stable enough to be used. It has yet to be truly battle tested, like with things like Storm and Spark. But in my opinion, you can probably take this to production just fine. We have plugins for talking very well to Datomic, SQL, Kafka. Our RS3 support is OK. But there's a lot of mediums that you can talk to quite easily. Onyx emits a vast amount of metrics to its own dashboard and arbitrary streams, so you can hook into Graphite. We have an automated cloud benchmarking suite that runs in AWS every time we release. We take performance very, very seriously, and we don't want any regressions, so we always test things like this. And we really do have production-grade performance right now. This was our last benchmark of Onyx. This is 5 C4 X-large EC2 instances on AWS, churning out consistently. This test ran actually for a couple hours, 500,000 messages a second. Totally fine, didn't experience any blips. And the next release that we're coming out with in the next few weeks pretty much blows us out of the water because we have some new advances. So we really are moving up, and this is already certainly good enough to be using for most use cases. So that's all I have. If you want to try it, there's a line again template that will instantly drop you into a really nice environment with like hot code reloading and baked-in idioms and things like this. So this will get you off the ground really, really fast. You can check it out on GitHub. We're on as an organization, or just come talk to us in Gitter. We really like talking to everyone. That's all I got. Thanks. Any questions? We have a garbage collection API. Presumably there won't be, for a smaller cluster that's running for a few hours, you'll have like a few hundred entries. So performance of the log isn't even critical, but if you run it for weeks and weeks, you can just call a GC function. And what actually happens is that the GC mechanism will go in and delete log entries and then figure out what the replica should be as of that point and then store it in its place so someone can immediately go to the replica and then start moving along. Anything else? This is probably one of the reasons that I like going with Zookeeper, is because that Zookeeper is a strongly consistent data store. Never really thought about it in terms of split brains. Usually think about that in terms of like databases. Sorry, I lost my train of thought. Yeah, I'll get back to you on that one. Sorry. Anything else? Yeah, so one of the things, we're on 06 right now. 07 is going to feature a Java interface. And beyond 07, we're looking at ways to break outside of the JVM. And one of the first things I want to do is try to look at the story for Ruby, because there's a lot of hurting Rails programmers out there. And one of the things we can do is take the same approach as Storm. Like you can use standard I/O to like ship segments back and forth very fast on the local interface. I'm not sure exactly what we're going to do yet, but it'll probably be something like that. Oh, yes, yeah, so it's me and I have a partner, Lucas Bradstreet, who actually works on this full time. And either him or I or both of us are available for consulting. Cool. Thanks, everybody.